The purpose of this lesson is to identify empirical and molecular formulas, define them, and then learn how to calculate them given lab data. An empirical formula is the formula for a compound that demonstrates the simplest whole number ratio of the elements. When we have written out ionic formulas in the past, for example, magnesium combining with oxygen, we've always simplified this. So we would not write out the formula as Mg2O2 because we know that we can actually simplify that there will be one magnesium atom for every one oxygen atom. So we actually would eliminate those subscripts. And the formula would be MgO. That's the simplest whole number ratio for magnesium oxide. Most of the time when we're working with molecular compounds, they're going to have variations of this ratio, and that is where we're going to look at molecular formulas. So a molecular formula is the true formula, and it states the actual number of atoms that are in a compound in real life. And these are always going to be, when we're looking at molecular formulas, they're always going to be examples where we're dealing with molecules. So where compounds have been formed because of the sharing of electrons rather than the stealing of electrons and then subsequent attraction due to charges like ionic formulas. So again, empirical formula, it's going to be the simplest formula, and molecular formulas can sometimes be more complicated. It can show ratios that are higher than the simplest version. All right, so some examples of that. CH4 would be the simplest version of carbon and hydrogen for this particular compound. Now, that's also the empirical formula for the next things here. So CH4 is the empirical formula of CH4, of C2H8, of C3H12, and C4H16. So if we look at C2H8 in comparison, all we did was we multiplied CH4 by 2. So we multiplied each subscript by 2. In C3H12, hopefully you can pick up on this, we multiplied each subscript by 3. And then in C4H16, we multiplied each subscript by 4. So basically when we're looking at molecular formulas, it's just a ratio that we're multiplying by to get a bigger compound, a more complex compound. All right, so just a quick question on that. Which of the following would not have an empirical formula of C2H3? So to be honest with you on this, what I usually do is I just look at one of the elements and then try to see if I can figure out the ratio from there. So C3H9, again, we're trying to get to C2H3. So if I were to try to go through and divide, I could divide this 3 by a 3. And whatever I do here, I have to do to this next one. So the formula that I would get if I simplified that down would be CH3, which is not C2H3. So this one would not be a workable example for that. In this next one, I would look at what can I divide by? Well, here I could divide each one of these things by 2. And if I do that, I get C2H3, which is a winner for our empirical formula. All right, in this next one, I could divide both of these by 5. And again, I would get C2H3. So that also qualifies. Next one, C8H12. If I divide everything by 4, I could divide everything by 2 in this case as well, but then I would have to divide by 2 again. So I would get C2H3. So again, this one qualifies. And then in my last example, I could try to divide by 4, but this would not work. So automatically C4H5 is the lowest ratio for that particular compound. So this would not qualify. That's basically how you can do that, a really simple check for whether or not something is an empirical formula based on the molecular formulas. Just simplify down the numbers and see if it matches what the empirical formula is stating. All right, so on to something that is a bit more complicated, and it's more complicated only because there's quite a few steps. Similar to other things you've learned in chemistry, however, even though there's a lot of steps here, it's a very orderly process. So there's gonna be like step 1, then step 2, step 3, and you're always gonna do the same thing on repeat. And so the more problems that you do with this, the easier it will become for you. All right, if we're gonna calculate an empirical formula given lab data, the first step we're gonna do is to determine the number of moles of each element present. And this is where your basic stoichiometry foundation will really come into play and really help you. In these problems, typically you're gonna be given the percent composition of each element in a sample. So that would have been collected in lab. And what you're going to always assume there then is that you have 100 grams of the sample. So let's say you had 50% of the sample was hydrogen, which is a lot of hydrogen. You would then convert that over to saying like, I have 50 grams of hydrogen. Because if you know grams of a substance, you can divide that substance by the molar mass and then get the number of moles. And that's the goal. Step 1 is figure out how many moles of each element you have in the sample. So that kind of takes care of part A and part B. And then number 2 is once you know the number of moles of each element, you're then going to look at all of the elements and the number of moles. And you're going to divide by the smallest number of moles that are present amongst the elements. And this is to determine the actual ratio of the elements that exist within that compound. Again, prior basic stoichiometry knowledge would lead you to understand that the subscripts in the compound not only reflect the ratio of atoms within the compound, but if you have 1 mole of the compound, it reflects the ratio of moles of the atoms in that compound. All right, this isn't always going to be perfect when you do this math. Sometimes the ratios are going to be really, really close, like 1.98. So we could round that to a whole number. We would round that to 2. But they're not always going to be beautiful and simple and perfect. And sometimes we're going to get ratios that are going to, or divisions that are going to be like something like a 1.5, a 1.33, or a 1.25. In those cases, what you're going to do is you're going to find something that you can multiply that number by that will get you close to a whole number. And then you're going to multiply everything by that number. So in the case of a 0.5, you're always going to multiply by 2. In the case of a 0.3 repeating, you'll multiply by 3. And in the case of a 0.25, you'll multiply by 4. Those are the 3 most common, messy fraction type things that we will be working with in these chemistry problems. The last thing that you'll do is you will write the formula using the molar ratios as the subscripts of the elements in the compound. So that sounds confusing. That sounds like a lot of work. Let's go ahead and do an example problem to show you that it's really not as bad as it might seem. All right, so here's our example. Methyl acetate is a solvent commonly used in some paints, inks, and adhesives. Determine the empirical formula for methyl acetate, which has the following chemical analysis. So we have something that's 48.64% carbon, 8.16% hydrogen, and then 43.2% oxygen. What I'm going to do right here is I'm just going to slide this up. I'm going to show you a method I like to use for this just because it helps me to stay super organized. And that is I like to write everything out in a list. So usually what I'll do is I'll start with the elements in the order that they're given to me in the problem, and then that is the same order that I will use when I write out my final formula. But I like to just make this list. I like to put out carbon, and then hydrogen, and then oxygen. I'm going to give myself a little bit of space to do the math. Again, remember that the first step is to try to get to moles, and if we're given percent, we're going to assume that we have 100 grams of that substance. So 48.64 is going to be 48.64 grams. And then I'm going to divide that by the molar mass of carbon, which is 12.01. Now when I'm doing this, I'm going to make sure that I am keeping quite a few of my decimal, like my numbers in place, and I'm not going to round super early. So this gives me 4.049958 something. So I'll just kind of go with that many. All right, in the next one, hydrogen, I'm going to go 8.16. divided by 1.01, which is the molar mass of hydrogen. And I get 8.079208. All right, and the last one here is 43.2%, so we'll say 43.2 grams over the molar mass of oxygen, which is 16.00. And I get, oh, a nice number here, 2.7. All right, so my first step is to take and convert from percent to grams just by assuming 100 and then divide everything by their individual molar masses. The next step is to compare mole ratios. So I am going to divide everything by the smallest number of moles that I calculated, which fortunately for us is 2.7. And it's fortunate because that means we just have to write down 2.7 instead of all those other numbers. All right, this one's pretty simple. That's going to be 1. This one should work out fairly simple. I'm going to get a 2.992299, so I'm going to round that to 3. Again, if it's close, you can round it to a whole number. And this gives me 1.49998, so this I'm going to have to round to 1.5. All right, now because I have that 1.5, I'm actually going to have to multiply everything here by 2, so I'll go ahead and do that right now. So I'm going to get a 3 here, a 6 here, and a 2 on the bottom. All right, now that I have those numbers, it's time to write out the actual formula of this compound. So the compound's empirical formula, again, this is not necessarily going to be the molecular formula or the formula that the literature will tell you methyl acetate is, but this is our empirical, simplest whole number ratio formula. So carbon is going to be 3, so it'll be C3, hydrogen has 6, and oxygen has 2. And that will be how we will solve these problems in the future. Again, a quick little recap. Usually they will give you percent. If they give you percent, assume 100 grams. Now, if the problem just directly gives you grams, then you don't have to do that step. You can just straight divide by the molar mass of each element. The next step then would be to divide by the simplest or smallest, mole that you have calculated, and you're going to divide everything by that. So one of your elements should have an assigned number of 1. And then if the numbers come out perfect, just write out your formula. And if they don't, if it was something like in the example problem we just did where it was like a 1.5, make sure you're not just multiplying that one by 2, but that you're multiplying everything by 2 to get that ratio that you need.